Hello, once again you are welcome to today's class, continuation of our biostatistics, and I believe you've been enjoying it from lesson 1. My name is Dr. Henry Isagboyin, and today we are continuing with lesson 6, case study on how to ensure an adequate sample size for detecting significant effects in case control studies. So we'll be looking at these steps, and I can assure you, you will enjoy this class. So let's proceed to it. Number 1, you want to estimate the expected effect size. You want to carry the research design, and you want to know what's the minimum number of respondents that you will need so that this research will hold waters. It can be used conclusively to evidently decide or take decision on behalf of a full community. So you have to check the odds ratio, because the odds ratio is typically used in case control studies to measure the strength of the association between the exposure and the outcome. So you need an estimate of the expected odds ratio, which can be based on previous studies or pilot data. So like I told you, check the previous studies and see 30%, 20%, 40%. You can now apply it. Number 2, small versus large effects. Why do we need to do a correct sample size calculation? Because there are issues of small size and versus large effect. Why? Large effect, example, an odd ratio of 5.0, which is 50%, requires smaller sample size to detect, whereas smaller effect, example, odd ratio of 1.5, require larger sample sizes. Number 2, to determine the control to case ratio. You have to determine the control to case ratio. Now, the control to case ratio, in this case, just simply explain that they impact the sample size. Because the case control case ratio impacts the sample size. For example, you want to check. This is the control. This is the case. Maybe our control will be 1. Our cases will be 3. So for every 3 persons that is exposed to the disease, we have to get 1 control. And this will impact your sample size. So a large number of control compared to cases can increase the statistical power. So if you are going to use 20 control, you know that your exposed population, that the other people who have the issues, who have been exposed to that disease, must be what? Times 3. If it is 1:3 or 1:2 and so on. So that's that. Now, the next one is more control. Now, this increases precision but may not always be feasible in terms of resources. Actually, the more control you have, the more better your research, because we'll be comparing with our research. You cannot be using 10 controls when you are using 100 exposed data samples. You can't. You have to make it commensurate. If you're using 100 patients, your control should be close to, let's say, 20 or 30 thereabouts. Now let's look at the other aspect. Number 3, specify the desired power. Power refers to the probability of detecting a true effect, if at all it exists. So a typical power level is 80%, meaning that there is an 80% chance of detecting an association if one truly exists. If one truly exists, you understand that? You remember your null hypothesis and your alternative hypothesis? Good. So you know what I mean. Now, higher power, 90%, requires large sample sizes but can detect even smaller associations. So we need to specify the desired power. That's why we need a good level of sample that affects the kind of sample that you are going to have. Now, another thing that affects it is to choose the significant level. Now, of course, when you want to carry out your hypothesis, I told you, commonly people use 0.05, and this is the probability of committing a type 1 error, that's false positive, where it is not. You understand that? And actually, it is not. That null hypothesis is that it is not having any effect. And then you now went to choose the alternative when actually it is not having any effect. Instead of you to choose, you did not choose the alternative. The null hypothesis, the original. You did not choose it. You went to choose the other, when in the real sense it has no effect. And you went to say it had effect. Because if you had chosen the type 1, it will show that it has no effect. So setting your p-value or alpha level at 0.05 means that there is a 5% chance of falsely claiming a significant effect when there is none. All you need to know is p less than 0.05 it is not significant. So we accept the null hypothesis. But p greater than 0.05, it is what? Significant. So these are all that you need to look into. It's very, very important. Just remember, so that I don't make a mistake, I remember you look at the other aspects, look at the previous where we talked about hypothesis. It's good. Now when p is less than, whether significant or not, just check it there, please, so that I don't make a mistake. But then when it is significant, you accept type 1. That is your null hypothesis. When it is not significant, it means you do not accept the HO, that the null hypothesis. You go for the alternative hypothesis. Very simple. Now, the smaller the alpha, the larger the sample size required to detect a significant effect. So that is that. Let's move on. Number 5, account for the expected prevalence of the exposure. Now, if you expect a high proportion of exposed individuals, you may need fewer participants to observe a meaningful effect. Number 6 is you use statistical software for calculation. For example, AP info, G power, pass, and so on. So if you have an odd ratio of 2.0 and a p-value of 0.05, which is alpha, and a confidence size of 80%, and a 1-to-1 case control ratio, a sample size calculator will give you the number of cases and the controls needed to detect a statistical significant difference. You have chosen all your parameters, yet you choose 1-to-1 case control. It will let you know the power size that you need. The next one, of course, that affects the population size is an adjust for potential dropouts or missing data. That's the next step. In case control studies, some cases or controls may be lost or fail to meet inclusion criteria. So always account for potential dropouts by increasing your sample size by 10 to 20% to maintain power. So when you do that, you have said, okay, my control size after calculating is 60 patients. On your own, you add a 20% attrition. So if you add 20% to 10% of 60 is 6. So 20% will be 12. So it becomes 12 plus 60. That now gives you 72. So your power size will now be 72. Although your calculated power size is 60, but so that in case anything happens, you will still be within the approved 60. So let the 12 on top take the burden. Account for the missing data, account for the unrespondent forms that you gave her that the people did not return, or you gave her they did not complete the data properly. And finally is the considering study design and practical constraints. You want to check the feasibility. While the large sample size improves statistical power, practically you want to see the limitation. Why? Funding, time, accessibility, and this may dictate what is impossible, and this may dictate what is possible. You may need to balance ideal sample size calculation with real world constraints. You want to do all this and all that, but check how many days do you have to do this analysis? How much do you have to be able to go there and get this data? You have to look at that. So it's very important to see the feasibility. Can I take this number of patients? No, I cannot. I can only deal with maybe this, that, and that. And then you go ahead and then you get those data and then you put them in. Now for matching cases and controls, if you plan to match cases to controls based on factors like age, sex, or other variables, this can reduce the sample size requirement, but it also requires careful planning to maintain statistical power. Yes, it requires good planning to maintain statistical power. So with the process of your research, you are careful to check your requirement carefully and plan properly before you commence, so that you can have the right power size needed and you don't get stranded in the middle of the research. So in summary, a good power size, to get it, you need to define the expected effect size, choose a control to case ratio, select the power level, set the alpha level, account for exposure and exposure prevalence and other study factors, use statistical software to also check, adjust for dropouts, account for that, the attrition, and balance the ideal calculation with practical constraints. I believe with what I have just said, you've now understood what needs to be done in terms of the decisions you take before you can agree on the specific power size that you need. I want to thank you for coming for listening to this lecture, and I believe that with this we have come to an end of your curriculum for biostatistics, and so I expect that you read from lesson 1 to this particular last lesson 6, and then you also check out for other materials that have been posted on the Google Classroom. Watch them again and again, understand them again and again, take notes again and again, ask questions when you need to, reach out to me when you need to. I'll be available to attend to you. Once again, you have no choice. You are to score the best in your exams. Why? Because everything you've learned, straightforward to the answer, you will find in the exam easily. You would be able to annotate, you'll be able to give diagram, you'll be able to give the formulas, you'll be able to explain these things properly. I can assure you, you are good at it. You are intelligent. You may not know, but I know it. And that's why I'm telling you, you are intelligent. Give it your best shot and never look down on yourself. If I could do it, you can do it also. If I could get a distinction in biostatistics in my days, even in my master's, my PhD, my first degree, you can. My research methodology when I was in first degree actually was a B, and you can do better than I did. I wish you all the best. I'll see you in the next semester. Thank you, and have a wonderful time preparing for your test, preparing for your exams. Bye.